Emergency. Dive, 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 dive. Fantastic. On Tuesday, for the exam, is it a certificate? On my surgery. That's unfortunately, because you're Thursday, I can't have you come on Tuesday. Right. But if you get here, you can grab a study room. Or an empty classroom or something. Yeah. Sorry, Trevor. I wish. All right. Oh, 30. Well, 30. A bunch of people in the waiting room probably all freaking out because I didn't hit admit yet. Yeah. Nailed it. All right. 12:30. Let's start. Lord, thank you for bringing us together this afternoon. Thank you for everything that you do for us. Pray that you would help us stay focused and continue to help us just do what it takes to succeed and thrive in this environment. In your name we pray. Amen. All right. Okay. The things and the stuff and the things. Numbers, Mason. What do they mean? All that. All of that. So, what we got? We're gonna recap and we're gonna do some problems. We're gonna do. We're definitely not gonna get through all these problems, right? These are a lot of problems for one day. We'll probably get through like two of them, depending. Um, mhm. Yeah. So you know what we'll even do? Let you guys choose which ones you want to do. Um, so recapping, great success. Right? Nothing was confusing. Oh, it's frozen on the inside of the classroom. All right, let's try this again. Great success. All right. Nothing was confusing. I'm gonna go home, guys. That's it. Thank you. Great. Tip your weight stuff. All right. Okay. So last class we talked about impedance. We talked about a little bit about the transfer function method and the Laplace transform methods, right? We did a little bit with that, but mostly we talked about impedance last class and how we can apply impedance to circuit problems, right? It's a specific idea in which we normalize the resistance of components, right? And so hopefully we remember from circuits that everything has resistance, right? Everything's got resistance. And so everything's got resistance, or wires have resistance. Right? Everything's eating our lunch. The second law of thermodynamics is real, and it wants to stomp you down, right? And eventually we'll win because, the eventual heat death of the universe is going to happen probably in the next billion to 2 billion years, somewhere in there, rough estimate, right? So live it up now, because when you turn a billion, you're going to really regret it if you haven't. Okay. But, right, so everything's got a resistance associated with it. We can model this using Ohm's law and Laplace domain, right? And all we did was we took the element equations that we had, right, our first order differential equations for capacitance, for inductance. We took the Laplace transform and we created the ratio of the voltage drop to the current. And that's what the impedance is, right? So we get LS for inductors, we get 1 over CS for capacitors, and just R for resistance. Okay? And impedance is nice because it allows us to collapse really complex circuits into equivalent elements and do a much simpler analysis. Right? All right. You guys have any questions from last time that you want to ask? Anything that anything that's confusing you that you really want to talk about? So the question was, is there any one topic that's going to be weighted higher than another? The problem section will be weighed more than the theory section. That's really all you're getting from them. It's okay. So general exam is going to look like the homeworks, right? So, and honestly, these problems that I gave you guys to do for this week are, some of them are above and beyond what I can put on an exam. The double pendulum is a 6th order system. 7th order if you put a step input in. You don't have enough time in 2.5 hours to run through the model and do the Laplace transform and do the inverse Laplace transform with partial fraction expansion. Right? It's a bear of a problem. And the algebra in it sucks. Right? It does. Right? But if you can do that problem, then you shouldn't be afraid of any of the other problems that you see on the exam, right? Same deal goes with the maglev problem that's on there. That maglev problem turns out to be a 5th order system, right? So really, realistically, a 3rd order system is like the tops. Right? A 3rd order system is like the sweet spot for testing you guys about stuff. Okay. So modeling. All right, we need to know state space, we need to know transfer functions. Right? Transfer functions are really important, right? Because the entire Laplace transform method, right, if we have 0 initial conditions, breaks down into the transfer function method. Right? Linearization. What happens if you run across something in the real world that's nonlinear, like everything? Right? Well, we need to know how to make it look linear. Well, we've got first order systems. What do I need to know about first order systems? How do we characterize a first order system? Another way of asking that question is, what is the standard form equation for a first order system, right? Because remember, our standard form equations, if we look at them, tell us what we can characterize the system with, right? They tell us the important variables for our system. How do you draw a first order system, right? We set up a little algorithm for the find the time constant, find the settling time, and because it's first order, just draw a nice exponential curve, right? Second order systems, right? How do we characterize a second order system? Right? Again, what's the standard form equation? What are the different root responses and what do they mean? That's important because, right, even if you're not specifically asked what do all the root responses mean, if you don't know them, it's going to be harder for you to do inverse Laplace transforms, right? how would you draw a second order system? We talked about that too, right? You need a little bit more information to draw it. Right? If I gave you the plot of the system response for a second order system, right? How would you find all the other parameters? Right? How would you recreate an approximate model for that? And then Laplace transforms, right? Initial value, final value theorem, and properties of Laplace transforms are all on the master sheet already. Right? That's just taking the limit for the first two, right? Taking the limit as s goes to infinity, taking the limit as s goes to 0 of s times f of s. And then, you know, we've got superposition, and the Laplace transform is a linear operator, so we can treat it just like a linear variable, right? We can distribute it, we can pull out the constant, right? When we take the derivative, where we have our nice generalized property for taking the derivative, where n is the order of the system, right? Okay. Inverse Laplace transforms means that you're going to have to know how to do partial fractions, right? That's important. Determine the system response using the Laplace transform method, right? So Laplace transform method is when we can't use zero initial conditions. So if you're given initial conditions and you're told to use the Laplace transform method, then you should use them when you take your derivative, right? Because remember, taking the derivative involves the use of the initial conditions. The Laplace transform method, right? But for the transfer function method, we assume zero initial conditions regardless of what we're told, right? So even if you're given, you know, x of 0 is 5 and x dot is 0, right? Yeah, you ignore it. You use zeros for transfer function. Okay. And then impedance, right? And we'll spend a little bit of time at the beginning of class recapping impedance, right? So impedance is just the specific application of Laplace transforms to electrical systems. Right? And it's a way for us to collapse complex electrical systems into simpler versions to analyze, right? Okay. You guys have any questions on the topics? I know I showed this last class, so it'd probably be a good thing to talk about now. Number 9 in the one that the worksheet that I gave you, or the homework. Okay. Trevor, we can run through that in a minute. Just you're gonna have to read me what the function is when we get there. I didn't bring my homework file with me. Actually, I have it on my computer. I can get it. Well, we can definitely do that. No, did you have a question? I'm gonna post them on Monday morning at 12 a.m. Well, I mean, I'm not gonna stay up and do it. I'm gonna set it on LoudCloud to automatically release them at that time. So once the homework is due, it will automatically. I might stay up, you know, just for the heck of it. Destiny 2 expansion came out a couple weeks ago. I gotta catch up. Got that raid race this weekend, so anyway, none of that's gonna happen because when you're adult and you have kids, you don't do raid races. All right. Anyway, cool. So test mods, right? Everybody's favorite mods software, mods website. I don't even know why they called it test mods, but that's cool because that's what it's called. And that's how we're going to take exam 2, right? And so what is different for you guys? What is different for you guys? Nothing. You are still going to take it on your computer. The only thing that changes is that instead of turning in your theory section in LoudCloud, it will automatically be captured on TestMoz. You just type it in the box, right, and you're good. And then the problems, you're still going to upload the problems. Now, how do we get in? Well, I'm going to post a link in the announcements. At the time of the exam, you will open that up. We'll still come to class for the first part, right? Still zoom in for the first part of class. We'll go over like some things. I'll try to make sure that everybody's at least in it to start at the same time. Because once you hit the start button, so the first page is like an instructions page. And then once you hit the start button, your timer starts, right? So once you get the first question, your timer on the bottom will tell you 2.5 hours, and it will constantly tick down for the rest of the time. So you don't have to look at the screen for anything in terms of time. You don't have to, you'll know everything just from the test prompt, okay? Once you get in there, in order to access the first page, you'll have to put in your student ID number. If you don't know your student ID number, you have a few days to get it. So there's that. All right. So yeah, all theory questions and test mods, unless otherwise directed, unless you were told specifically to upload something for it, don't worry about it. Do all the problems by hand. Turn in a PDF or a Word doc. Yeah, just. That is going to be in LoudCloud. All right, so you will turn in your PDF or Word doc into LoudCloud. Under the exam Dropbox, right? You'll get 30 minutes from the end of the exam, all right? So basically, if we start, like last time we started like 10, 15 minutes late, something like that. So you know, we'll just carry over the 30 minutes from when the actual start time. So if we started at 12:45, we get till 3:45, so we get the full 3 hours. All right, so make sure your document's legible, right? I'm not talking about handwriting, right? I'm not saying that, well, I mean, please try your best with handwriting, but the quality of your pictures, right? That's what I'm talking about, right? Like, please look at it before you turn it in. Don't just throw them on the thing and say that's going to be good enough, right? Because sometimes they get blurry and it makes it a little bit harder to grade, right? So make sure you got like a 4K camera, right? Really crisp. If you don't have one, please go out and buy one immediately. And anyway. One picture per page, formatted in portrait, please. Don't mosaic all of your pictures on one page and make them super tiny. Not appreciated. When you start the exam, the first page is the instruction page, right? On the instruction page, if you do not have your master sheet already printed out, or a Laplace transform table, like the one that I put in the announcements already printed out, you'll be able to click on a link that will automatically download the Word docs for you right then and there, and then you can open them on your computer. Okay? If you already have one printed out and you don't want to use the electronic version, that's fine, as long as yours doesn't have any notes written. Okay? Good. Once you click start, your timer starts. Okay? So basically, the question is asked, do you still have to log into Zoom and do the whole workspace sharing and such? And I would prefer that. Now, I understand that Wi-Fi networks, especially around the holidays, are not the greatest all the time. And so if you start to notice that you're having hiccups, right, just shoot me a message in the chat, like a private chat, saying, hey, I need to turn off my cameras because otherwise I'm going to lose these. Okay? And that's fine. And or if you notice earlier in the day, right, before you start taking the exam, when you log into class, let me know. Okay. If your Wi-Fi cuts out mysteriously, right, in the middle of the exam, I'm going to need you to get Cox to call me on the phone to tell me there's an outage. We'll figure something out. Okay. So you'll have to take the exam at some point over Thanksgiving weekend, likely, but we'll figure something out. Okay. Okay. Does you have any other questions about like logistics and stuff, right? Like I said, just sign in the class like you normally do, and then we'll do the pre-class stuff, and then right, we'll do the next, we'll start the next chapter of the story that goes with the quiz or the exam, and we'll go from there. No. I don't know what. Good question. What do you guys want if for your incentive? Um. Okay, that's very specific. What if I just got like gummy bears, like, and everybody got like a little package of gummy bears? How about that? The sugar freeze? You guys don't want? You don't want that? The Haribo sugar free gummy bears. Oh. All right, so all right, it sounded like gummy bears, I guess. So gummy bears are fruit snacks of some kind, some sort of candy treat will be provided if you can hit the threshold this time. Excellent. All right, cool. Anything else? Okay. Here's the Tri-Quizzard standing as of last week's. Right, we've got the Zoom engineers, Dr. Z sanitizers, uncalibrated calipers, Quizzard lizards, Michael Scott Paper Company, In the Bag, Zero Division, Doctors Without Doctorates, Life Livers, Warzone, SDCK, Yikes, the Swarm Lords, 185.31, Matilda's Pointy Compass, Static, Waffles. Remember, this week's points hinge on your meme creations. Please send those to me for tonight at midnight so I can put them in a PowerPoint that is dissociated from any student names, right? Just the PowerPoint just says your team name and then shows your meme, right? And then the other professors are going to look at them and rate them. The ones that I've seen so far have all been really good. So I'm glad that I don't have to judge, and please leave it at that. So there's that. Okay, so we covered the meme stuff. Next week's points are going to be tied to the exam in the way that the last exam worked, right? So your whole team gets averaged together, and then top score gets first place points, and so on and so forth. Okay. So I made this announcement in the other class. I'll make it in this class. It's not really hasn't been an issue at all, but I just wanted to reiterate it. After Thanksgiving break, if you are not in class, right, if you are on the Zoom session and you do not have your camera on without adequate reason for having it off, I'm going to just kick you from class. So, you guys need to, I mean, I realize we're more than 2/3 through the way through the semester, right? But you're not helping yourself by just showing up to Zoom meetings and turning your camera off and doing whatever, right? So I'm going to start taking a harder stance on that, right? Like I said, though, right, if you have a legitimate reason, right, like your Wi-Fi is bugging out or something, just let me know and we'll talk about it, right? That'll be fine. Okay. Awesome. Yeah, no, that's fine. Yeah, if you have to use I'm talking about like if you're sitting there for like 20 minutes with no camera on, like we're gonna. That's a good question, Taylor. I don't know if I'll share all of them. I'll definitely share the winning ones. We'll see. We'll see how much time we have. We'll see how much time we have. Because next week we're not gonna have time to look at the memes. Maybe I'll just post the PowerPoint with the memes. That's probably the. I'll post the PowerPoint with the memes in. I don't know that I want to put that on Live Cloud, so I'll put that in Discord. Put that in Discord, okay? And and then you guys can do that. So let's watch this video about inverse Laplace transforms and partial fractions. I wonder what it's about.
We're going to do a inverse Laplace of s plus 4 over s squared plus 2s 3. And notice on the Laplace table, there's no retreat of inverse this way, right? But if you notice the denominator s squared plus 2s minus 3, we can factor that, isn't it? So let's go ahead and factor this, and we will get s minus 1 times s plus 3, isn't it? Well, in this case right here, we can use partial fractions to break this apart. So this is going to be, let's put down the inverse Laplace. And for the first
figure out this constant, as you can see, the denominator is s minus 1, and all of my s are in red, okay? Anyway, I will come back to the original. I will cover up the same exact denominator, namely the s minus 1. And you have to ask yourself, how can we make this factor equal to 0? Well, we have to plug in s is equal to 1, isn't it? Okay? Then plugging 1 into this s and that s, but don't do it right here, right? So with that being said, you see we have 1 plus 4, which is 5. On the top, we have 5 over. On the bottom, 1 plus 3, which is 4. This is 5 and then over 4, right? And this is an s. This is the constant that we have. And now let's do the same right here. I will come back to here. I will cover this up. Well, how can I make this equal to 0? I have to have s is equal to negative 3, isn't it? Well, on the top, negative 3 plus 4 is going to be positive 1. So let's put down 1 and then over. Plugging negative 3 into here. Negative 3 minus 1 is negative 4. So we have 1 over negative 4, like that. All right? And now we figure out the constants. We can, of course, do this. I can take the constant to the front if you like. Let's put down 5 over 4 like this first. And then look at this as 1 over s minus 1. Well, the Laplace of what will be 1 over s minus 1. We know that has to be e to the 1t. In other words, just e to the t, right? And then for this, let's go ahead and take this to the front. So we have minus 1 over 4. And then look at this as the inverse Laplace of 1 over s plus 3. Since the bottom is just linear, we just have to have e to the something again, right? This is the same as saying s minus negative 3. So we have to have e to the negative 3t, just like that. And this right here is it. So this is one of the situations that just use partial fractions, so you can break the fractions apart, and then you go ahead and do this and that. That's it.
All right, sorry about the sound hiccup. But I think you get the point, right? All you missed was the factoring part. So that guy used the residues method, right? Or the cover-up method, or however you want to call it. And that's fine, you guys can do that, but as you know, that's not the way I do it, and both are fine, both are equivalent, right? So whatever you're most comfortable with, just do it that way. All right, so we're into the problems part. Now, give me 1 sec. I gotta pull up my problems sheet. Now, I'll let you guys pick. Do you guys, I know what Trevor's vote's gonna be. Do you guys want to do Trevor's problem, or do you want to do one of the other problems first? Since Trevor asked, we'll do Trevor's problem first. I gotta pull it up though. So 9C, that's the one you're, 9E. Ooh, fancy. All right, give me 1 sec to add a slide here. Let's not take that long, right? All right. I didn't go crazy with the slides at all. All right, so this is 9E. I almost wrote C again. 9E from homework number 5. So what are we asked to do, right? We're asked, given the following input-output equations, obtain the response, right? So we were given the input-output equations, we're given the initial conditions, and we're given the input, right? So what's my equation? It is 20 y double dots plus 80 y dots plus 260 y is equal to 0.8 times u of t, right? And I'm told that y of 0 is equal to 0, y dot of 0 is equal to -1, and u of t was equal to 10 delta t. All right, so when you see the little squiggly snake lowercase delta, right, that is telling you that it is a Dirac delta function. The Dirac delta function is our impulse. So this is an impulse input, right, with magnitude 10. That's what it's telling us. So the first thing we have to do, right, is we've got to take the Laplace transform of all of these, right? We'll take the Laplace transform of everything on
Dr. D,
yeah.
you took the y and y naught from problem 9C, not 9E. It's 0.02 and 0.6.
Thank
Or
you.
0.2 and 0.6, I mean.
Yeah. Awesome. Thank you. Good thing we didn't get all the way through and try to do it that way. Right, so I've got to take the Laplace transform of all these things, right? And I've used different colors on purpose because I'm going to do each one in a different color. So hopefully it's clear which one is which, right? So what do? We got 20 times, this is the same as 20 times the Laplace transform of y double dot, all right? Which is d squared y dt squared. Right, second derivative. Well, we've got a property for that, right? Property of our Laplace transform is going to tell us that this is going to be 20 times, well, the second derivative, so that's to the 2. So if I go through my property and I use n is equal to 2, I'll get s squared y of s minus s times y of 0 minus y dot of 0. Right? And that's what we'll get out. So we can combine this, right? So we're going to have minus 0.2s minus 0.6, right? Oh, sorry. I got to multiply that by 20. There we go. All right, so I multiply each term by 20. So 20 times 0.2, last time I checked, that should be 4. Okay. And 20 times 0.6 should be 12. Still got it. Still got it. All right, so that's our Laplace transform for 20 y double dot, right? So we take the 20 out, remember, and we've seen this when we did them by hand, right? When you take the integral of 0 to infinity of your function times e to the negative st dt, right? You end up, because that's what the definition of a Laplace transform is, I can take my constants out, right? The constant comes out, I use my property. The green one is the same as 80 times the Laplace transform of y dots. Well, using my using my properties of Laplace transforms for derivatives, I get this. I can multiply through by 80 and include my, so that's going to be 80 times 0.2. And, yep, minus 16. Okay. And then the last one on the left-hand side is just 260 times the Laplace transform of y, which is just going to be 260 times y of s. Sorry, we have to put 260. 260 times y of s. So far, so good. Any questions? Everybody following? We're doing all right. Okay. The last thing we have to do is take the Laplace transform of the. So 0.8 and 10, right? 0.8 and 10 are both constants, right? So 0.8 times, so what this is saying, right, is that the input is 0.8 times 10 times delta of t, right? Times the Dirac delta. So really, this is the Laplace transform of this times 8, right? Because 0.8 times 10, and 80% of 10 was 8 the last time I checked. And we can go to the Laplace transform table here, right? So what does our Laplace transforms table say is the Laplace transform of delta? Remembering that this is the unit impulse. I think I might start carrying my microphone around like that guy in that video. Pretty sweet. Might be the play. This is one. This is one. So the Laplace transform of this is 8 times 1 or 8. And so let's put it all together. Right, so instead of 20 y double dot, I'll have 20 s squared y of s minus 4s minus 12 plus 80 times y dot, which turned into 80s y of s minus 16 plus 260 y of s is equal to 8. Combine our like terms, get all of my y's on one side, everything else goes on the other side, right? If I do that, I'll get 20s squared plus 80s plus 260. Right. No, just for funsies. Right. So we can see where each one came from. Right. There's y of s. Okay, that's cool. Is equal to 8. Well, we're going to have, what, 8 plus 12 plus 16. So 8 plus 12 plus 16, right, that's 36. 8 plus 12 plus 16.
What happened to the 4s?
I'm getting there. Plus 4s.
Right.
So impatient. Gee. Right. So plus 4s. Trying to stick with the colors. It's not going to last another slide. All right. So now we've got this right, and we've had, because we did this. This is the Laplace transform method, and because we use the Laplace transform method, we put in the initial conditions, and because of that, now we have this term on the right-hand side that is our input plus our initial condition, right? Plus the effects of our initial condition. So our input, right, which was 8, plus the effects of my having these initial conditions, which gives me that 4s, and the rest of that gave me the 36, right, the 12 and the 16. Okay. So this is looking pretty good for us, right? So let's run it through, right? So we'll solve it for y of s. We'll solve it for y of s. And I'm running without notes right now, guys, so bear with me for a sec. I gotta grab it. So y of s is gonna be 4s plus 36 over 20s, right? So 4s plus 36 over 20s squared plus 80s plus 260, right? That should be what it is if memory serves correctly. I hope it does, because if it doesn't, that's a significant problem. So I literally just looked at it. Where are my keys? Nope. No. Anyway. All right, so we got something like this. So I'm gonna play around with this for a second, right? Because I can take 20 out of the denominator, right? So I can do this. And I can say, well, if I remove 20 here, I'd have s squared plus 4s plus 13. 13. No, but so I can do that. And I'm actually going to take it one step further. I'm going to take it one step further here. And I'm going to divide the numerator by 20. So I'll end up with 0.2s plus 1.8 divided by s squared plus 4s plus 13. And this is what y of s equals, right? All I did was a little algebra to kind of clear the s squared. Why would you want to do that? Well, remember, what's standard form for a second order equation, right? It's s squared plus 2 zeta omega n plus omega n squared, right? So this is in standard form for us. And there's advantages for us having it in standard form, because you can tell a little bit about the system response, right, if you wanted to. But we're just going to end up factoring this right now. Well, not factoring, but we're going to find the roots, right? So what are the roots here? What are the roots? Uh-huh. So if you solve for the roots, you get a complex conjugate pairing, which is probably everybody's favorite root to see. I like it more than multiple roots, or more than double or triple roots. We also know that it's stable, right? Because the real part is negative. So that's nice. So what does this mean, right? If we have complex conjugate pairing, what does this mean for our system response? What are we expecting to happen? What are we expecting to be? Is that no? It's a, you gotta complete the square, sure, but why? What kind of response, like what's the shape of the curve? So I heard Trevor and Noah both say things that were both right, but I don't know if you combine what you guys. Trevor, what did you say? You said yes, underdamped sinusoid, right? It's a damped sinusoid, right? It isn't underdamped response, right? If you have complex conjugates that are stable, you'll get this nice damped sinusoidal curve, right? And because we know that it's a damped sinusoid, we know that we want our Laplace transform to line up, right? Or our inverse has to line up with this, which is omega over s plus a squared plus omega squared, or cosine omega t e to the negative a t s plus a over s plus a squared plus omega squared. Right? And those should line up. I don't think I did them backwards. Sometimes I do them backwards for memory. Right? The Laplace transform table exists for a reason so that I don't have to cram that into my brain and push something else out that's more useful. So we want solutions that look like this. And as Noah said, that means we need to complete the square. Right? Because why? Because look at the denominator. The denominator is in a very specific formula. And we are going to assume, well, we're not going to assume, we are going to construct our solution to be of the form of a sine and a cosine. Right? Sine plus cosine. Because what we have doesn't look like a pure sine wave, and it doesn't look like a pure cosine, right? It's in the middle somewhere, right? So let's complete the square here. Right? So I'm gonna erase this, so I have some room. But that's on the table anyway, so we should be good. So I can say that this equals 0.2s plus 1.8 divide. Well, if I'm going to complete the square, right? This is going to be s squared plus 4s. Well, I take half and I square it. So that's going to be plus 4. And what's left is, I'll call it 3 squared. Or 9, depending on how you like to roll. But there's a reason why I want to call it 3 squared, right? Because now I know what omega is directly. So I can algebra this a little bit more, right? And this will be what? S plus 2 squared plus 3 squared. And now I've got it, right? A is 2, omega is 3. And we want that because in the next part, we are going to set this equal to the damped cosine plus the damped sine responses. So we need to know what omega and A are, right? And then we can solve for our coefficients. So let's rewrite it. 0.2s plus 1.8 over s plus 2 quantity squared plus 3 squared. And that's going to be equal to, I'll use capital A times 3 squared over s plus 2 squared plus 3 squared plus capital B times s plus 2 over s plus 2 squared plus 3. Right, so where did that come from, right? That's just from the Laplace transform table, right? That's sine and cosine, the thing that I just wrote down and erased a minute ago, right? Damped sine and damped cosine. So now we just need to figure out what A and B are, and we're pretty much in the clear, right? Pretty much in the clear. Thank you, Noah. Appreciate it. I didn't see a square there anyway. Come on, you can't go back on the video and find it for all time, forever. No, yeah, it is. It is not omega squared. It's just omega over. All right, so once we have it here, right, what do? We multiply through by the denominator. And this is a nice one, right? Because we don't have any other roots, because our input was an impulse, it doesn't affect the dimensionality of our system, right? If we had had a sine wave, then we'd have an extra s on the bottom here, right? Because, or I'm sorry, not a sine wave, a step. We had an input step. We would have had an additional 1 over s in this, that everything gets multiplied by, right? Which doesn't gunk up the works completely, but it adds a constant that we have to solve. Right? If you had a ramp, right, something times t, right? T gives you 1 over s squared, right? So that increases the dimensionality by 2. Right, so instead of having a second order system, you've got a fourth. So you've got to solve for C and D as well. So, but this being in this form is really nice because this is going to be a direct solve for us. Right, so let's do it. Let's multiply it out. And if we multiply it out, we'll get 0.2 s plus 1.8 is equal to 3 times a plus b times s plus 2b. Right? Is that correct? Did I hit all of them? I didn't mess it up. BS plus 2b. Yeah, we good. Okay. S to the 1. So grab all of our S terms. Well, on the left-hand side, that's 0.2. On the right-hand side, that's B. Nailed it. Done. We got B. S to the 0. Okay, well, we got 1.8 on the left. We got 3A and 2B. 3A and 2B on the right. We know B, right? We know B. Throw it right down in there. We're good to go. All right, so B was 0.2, so we got 0.4, 1.8 minus 0.4 divided by 3. Because obviously, without having to use a calculator, 0.46, repeating. So I'm going to. Right, so y of s is equal to a, which is 0.467 times 3 over s plus 2 squared plus 3 squared, plus 0.2 times s plus 2 over s plus 2 squared plus 3. And if we take the Laplace inverse of this, well, the inverse Laplace transform of y of s is y of t. We already know that this is the sine component, right? So this is going to be 0.467 e to the negative 2t sine of 3t plus 0.2 cosine, oh, sorry, let's keep it straight here, e to the negative 2t cosine of 3t. No. Well, I mean, I guess technically fraction would be more accurate. Unless you want to write million. But for in terms of the answer, no. Yeah. Well, yeah. There you go. So yeah, so if you wanted to test this out in simulate and see what it looks like, you could use this for transfer function. For this particular one, because we didn't find a transfer function, right? You would use an integrated loss method. So you would take this y of s equation. Well, if you go back up before you do the partial fraction, and you see how everything shapes out. Okay. Any other questions? All right. So no other questions. We can go to the other. Who was supposed to do the first question from the sheet? Let's see. I swear, Zoom. I swear. Okay. Yeah. According to my sheet of example problems, Chris, you were supposed to be responsible for this one. So, how we doing?
Yes. Okay, so I've gotten it. I'll just show what I have here. There we go. So this is as far as I've kind of gotten.
Oh,
So I've got the sketch here with the resistor and the inductor and then the conditions there. Input is our E in, the voltage, and then output is the IL there. And then the truths, we have the ER, the Ohm's law, and then EL equal to L, I dot L. And then the KVL for that is those three things. Then with the reduction, the EN is equal to the ER minus the EL. I put those on the other side. And then I just subbed in those values and I got it to look like that. And that's about as far as I've gotten.
okay. Well, you got the model, right? Which is good.
Yeah.
Awesome. Cool. Did everybody follow that? Perfectly, no problems, right? Okay, so let's run through it real quick, right? So, right, so you can do this a couple ways. I'm actually going to show you how to do this with impedance too, just in case you wanted to know, right? For no other reason than just in case you wanted to know, right? Because we should get the same thing both ways, right? So it shouldn't matter. Maybe I'm going to do, yeah, there it is. Got it. All right. So what do we got, right? Excellent. En plus minus resistor inductor. Right. We've done, I don't know why I made that a T. We've done the RL circuit a lot of times, right? So this is kind of, hopefully, we're good seeing this, right? So the way that Chris did it, I don't know why I wrote E out. I'm not paying attention to what I'm doing. All right. Right, so we've got our truths, right? And the way that Chris did it is the standard way that we've been doing it, right? We define our KVL. We've got E in is equal to ER plus EL. We've got EL is equal to L, I dot L. IC is equal to C, E dot C, right? And well, I don't know why I would put that there. Sorry. Dr. D's brain is not working. There we go. Got it. Got it. We also know that E in of T was equal to 0.8 delta of T. We just went over talking about what the delta is, right? But if you ever see the delta, right, that's just telling you that it's an impulse input. And that's the delta is the unit input. Okay. We were given some initial conditions as well, right? Is it 0.08? Doesn't really matter. 0.08 delta of T. We're gonna go back for a second because we were given initial conditions, right? But our initial condition is that it's 0, right? So the current is 0. One time is equal to 0. So we're basically just making the transfer function here, right? We don't. That's where we're at. Excellent. So we can run through this. I do it this way. For later, we're going to want ZR is equal to R and ZC is equal to 1 over CS for later. When we do this, we create the model using impedance. Right? I'm going to reduce this equation. We will get E in is equal to L I dot L plus R I sub L.
Dr. D, for the impedance equations, did you mean to do the inductor equation instead of the capacitor equation?
I did. I was testing you. Passed. Congratulations. Sorry, guys. You can stay on your toes. All right, you gotta stay on your toes in these parts. Keep your head on the swivel. Sorry. All right. So there's our model, right? That's it. That's the whole system. So what do we need to do now? We'll take the Laplace transform of the whole thing. We have 0 initial conditions, right? We have 0 initial conditions. That means that we just need this, right? We have E in of S. And we have that. Now I skipped an algebra. And I didn't do the property, right? When we don't remember, when we have the properties, first order derivative, right? In Laplace, it's going to be S times Y of S minus Y0. Y0 was 0. I0, right? So we're just left with S times I of S. Right? And then I just regrouped my terms. So like this. I know what En of t is, right? So I can do this, right? The Laplace transform of En of t is En of s, which is just going to be 0.08 is equal to Ls plus R times IL of s, right? Specifically asked here to find what was asked for? Obtain the current response I of t. If I want the current response, I know L, right, and I know R. I just plugged in and divided by Ls plus R. I have an expression for IL of S.
Were the values for L and R given?
They were in the problem statement.
All right, I didn't see that. Thank you.
And remember, right? This is in ohms, right? This is in ohms. Right, so there we are. And what do we do from here? Well, we do we're going to simplify this a little bit for a second. Okay? Because you'll see. This. And so let me rewrite that function on the next slide. All right, whoa, what's going on? That part of the screen's haunted. Don't worry about it. All right. This is what IL of S is, right? But I'm gonna divide out by 0.02, right? So I'll get 0.08 over 0.02 times S plus 60, not 4. I don't know why. 4 over S plus 60. Now, hey, that looks like something on the Laplace transform. I don't even have to do partial fractions. I can inverse this one right away. So if I take the inverse Laplace transform of this, I will get I sub L of t. This will be 4 times e to the negative 60 t amps. What if I was like, you know what, I really want to do this with impedance instead, because impedance is the new hotness, and we just learned it, and I'm really excited about it, and I want to feel cool by using impedance. So we can, sure, let's do it. Let's do this with impedance, right? We should get the same answer though, right? Because otherwise we don't have equivalent methods. We should get the same system response out. So let's go back. Let's talk about impedance. Well, everything here is in series, right? So even before that, right? We did everything from this equation, right? That's where we started. We started with KVL. What if, I'm going to take the Laplace transform of this, right? So I'll get En of S is equal to ER of S plus EL of S. Okay? Now, what if, now just imagine for a second that I divide every term. I divide both sides by the current. What do I get? And now I've got impedance. So it turns out if you write down KVL, it's equivalent in the Laplace domain as, I don't want to call it KZL, but I almost do want to call it KZL. It's not really a thing. But it's the same as writing impedance. Like you can write the impedance terms for everything in your loop, right? It's the same deal. So if I do this, right, this is just what we'll call Z in of S is equal to ZR of S plus ZL of S, right? So this is, what is this? This is going to be R plus LS, right? And that's equal to E in over I of S, but I want I of S, yeah? Well, let's do it on the next slide. Right? So E in over I of S is equal to R plus LS. Right? I'm going to multiply by I of S and divide by R plus LS. And so what I found was that E in over I of S was equal to R plus LS. I'm going to solve this for I of S, and this will give me that E in of S, right? Oh, hey, that is exactly what we got when we did it the other way, right? Because this is 0.08 over 0.02 times F plus 1.2, which is equal to 4 over S plus 60. And if I take the inverse Laplace transform, I of t is equal to 4e to the negative 60t. Yes. Grade 6. Question. What is the time constant in this system? This is 1 over 60. What is 1 over 60? You can get that from two places. Get that from two places. First of all, if I rewrite this in standard form, it would be this. And 0.02 divided by 1.2 turns out is 1 over 60, 0.016667. Or you get it from here, right? How much time does it take me to offset that negative 60 so I get negative 1? It should be 1/60th of a second, day, month, year, hour. I like 1/60th of an hour. Right. Millennial. Is there any questions?
I have a quick question.
Mm-hmm.
So this might be obvious, but so when do we use the parts method separation, and then when, because like on this one we didn't, but on the last one we did, and I
Right.
don't.
All right, Chris, good question. So we use the partial fractions when we have to. This one just happened to come out in the form that we already have from the table, right?
Oh yeah.
Blake,
Okay.
it's rough, Blake, because I have to teach back-to-back classes. So if I don't drink enough coffee in the morning, I miss my chance. So it's just a rough day. Chris, I'm sorry, I cut you off. Were you saying something else?
Oh no, I was just saying that makes sense. Thanks.
Yeah. So yeah, it's whenever. Essentially, right. Another way of thinking about it is you'll always have to use it when there's more than one root for a system. So for a first order system, right, we already know that all first order systems have this exponential behavior, right? They're either going to exponentially grow out of control or they're going to be exponentially stable, right? That's just first order, the nature of first order systems. When you have something like a second order system, that's when we need to start looking at the root responses and figuring out what's that telling us about how our response is going to look. Okay. Any other questions? Yeah. Perfect. Okay. So I want to do, no, I don't want to do that one. All right, so here's the deal. Here's the deal. I don't want to do the maglev one. We did it in the last class, and there's already a video of it, right? So if you guys watched the last class, like the lecture from this morning, you would see how to do that one. right? So why don't we do a different one so we can spread out how many examples actually got worked out today? Unless you guys really want to do Maglev. Also, let's not do the double pendulum. That problem will take us the entirety of the rest of class to do. That is a beast of a problem. And the algebra sucks. It sucks. Okay. It's a sixth order system. It's going to be like a seventh order system, right? Because there's a step input on it, and it's too much. It's too much. But if you can do that problem, I get like you're straight. You know how to do all the things that are related to Laplace transform, right? All right. Do you guys have a specific problem that you want me to do from the sheet? Op amp? What? Oh, okay. Yeah. Okay, the big circuit one. All right. We'll go with big circuit. All right, the big circuit problem. Let's find it. Just so this one, if you guys watch the 945 lecture, we went through this one. Most of the problems, so that first one that we just did, that one is not too bad, right? I would say that conceptually, I will say this, conceptually, none of these problems are super difficult. The thing that's going to get you is that they are time consuming and you have to be meticulous with your algebra. Those are the things that are going to get you. And so that's why I did the whole thing at the beginning of class. That's the intermission video. This one is just, I don't know what I was thinking. There's a transfer. All right. Use the impedance method to find the model for this system. Report. It says report all the transfer function, which is great grammar. We're just going to report the transfer function. It says report all the transfer functions. And you can certainly do that. But what we're going to do here is we're going to assume that we've got terminals here. Okay. I'm going to assume that I've got to put terminals. Okay. I know that's not in the diagram, right? And I apologize. It says on my sheet that Hannah, you're going to lead us out of the darkness on this one. But it says that. Guess not. Looks like she's not. Okay. Well, we'll just get started then. Right. So I'm going to assume that I have some. Assume that I have some terminals there. I'm reading out this voltage drop across this central resistor. Okay. I want the transfer function, right? And I want to use the impedance method. Fantastic. Let's do it. Let's redraw our circuit. What is going on? Haunted. This podium is haunted. So this is a problem off of the first exam as well, all right? All right, so this is my E out, is this voltage drop between these terminals. Okay. And just for completeness, right, I've got two nodes here, A and B. IR1, IR2, IL, IC, IC. And 2 KBLs left-hand side and right-hand side. That's what I've got. It specifically tells me to use impedance, right? So I better use impedance. I've already put these in the Laplace form, right? My input and my output. We got impedance. So ZC is equal to 1 over CS, ZL is equal to LS, ZR is equal to R. Similar to the one we did in class the other day, right? If we're using this E out, we can tell that E out is just R2 times I. Right? I guess it's IR2. All right. So I would ask for the transfer function of E out to E in, right? That's what I want to find. So if I'm going to do this with impedance, first thing I'm going to do is I'm going to collapse this branch. These are in series and they share the same current. So I can add them in series, right? So this is going to tell me that ZEQ1 is equal to ZC plus ZR, which is 1 over CS plus R, which is RCS plus 1 over CS. Guess that's R3, right? We should probably be consistent with our naming here. Okay, so we got that. Found my equivalent impedance. So I'll draw my new circuit. All right, I've still got A and B. All right, this is still I, R1. We know that this is still IC. All right. All those currents are still different. So now what do we know? Well, these two branches have the same voltage drop, huh? Yes, good. Since they have the same voltage drop, we can add these in parallel. And we can make ZEQ2. And ZEQ2, right, is just equal to 1 over R2 plus 1 over ZEQ1. And so let's call it this, right? 1 over ZR2, which is 1 over R2 plus, we'll 1 over ZEQ1 would give us CS over R3 CS plus 1. Which, if I do the algebra, remember this is 1 over ZEQ2, right? 1 over ZEQ2. So I gotta flip it. ZEQ2 is really R2 times R3 CS plus 1 over R2 plus R3 times CS. So I can redraw. So I can redraw my circuit again. I redraw it, right? This time across, and look at what I've got out here. This is a single branch circuit, right? I've gotten rid of all of those. Now everything has the same voltage or the same current, right? Everything just has iron, which is much nicer, right? So I can actually add all of these together, right? Because I can get E of S over I of S is equal to ZR1 plus ZEQ2 plus Z sub L, right? Which is R1 plus R2 times R3 plus, no, R3 CS plus 1 divided by R2 plus R3 CS plus 1 plus LS plus R1. Not R1, not double R1. That's all my notes. Okay. So now we're going to algebra this and we're going to come up with common denominators, right? Great. What's our common denominator going to be? This whole thing over here. R2 plus R3 times CS plus 1. So I'll multiply R1 times that and R2 times a fraction of that on top and bottom. And if I do that, I'll get this really super not gross looking function. Right? That's obvious that that's what that would be. There. At least the denominator is manageable. That's great, but that's E in over I of S, right? And what I want is E in or E out over E in, right? But remember, we came up with our function for E out earlier. Right? That's just I times R2. And so I times R2 is equal to E out, right? So E out is equal to I of S times R2. So I of S is equal to E out over R2. So now here's where the fun part happens, right? Because if I want E in, I can get E in over E out, right? Because I can plug in that I of S is equal to E out over R2. So this is the same as E in over E out times R2. And that's going to equal that whole big old thing, right? The L R2 plus R3 CS squared plus LS plus R1 R2 plus R3 CS R1 plus R2 R3 CS plus R2 over R2 plus R3 CS plus 1. Okay. So I have to divide everything by R2. So instead of making more work for myself here, I'm just gonna go ahead and do that. And that's done. Except that it's not done because I have E in over E out, so we gotta flip this. Right? So E out of S over E in of S is equal to and now we got it. So hey, look at that. We ended up with a second order differential equation on the bottom, which we should have expected because we've got two energy storage. What's on this? About an hour. Okay. So we've done a transfer function method. We've done an impedance. Right? Why don't we try a Laplace transform method? How about that? So the only one that's in the packet is the sixth order system. We're not going to do that. But what we're going to do is we're going to do this one, but I'm going to make it a Laplace transform method problem, right? So we're going to say that I of 0 is equal to 2 amps. And we're going to say that X of 0 is equal to 1, and X dot of 0 is equal to 0.5. Right? This is meters. Question is asking us to use the Laplace transform method to determine the displacement of Dirac x of t. Right, and I'm not going to run through how to do the model. Well, I guess technically, yeah, you could run through it. May as well. Who was supposed to do this one on the sheet? Jake. Jake, what you got? You got anything?
Yeah. That was annoying.
One sec. Everybody mute in the classroom if you're on.
See if you could see it.
Yeah, give me one second. I'm gonna turn this. There we go. All right. All right. So walk us through what you did.
All right, so I just drew out the circuit and then I kind of like combined the free body diagrams on that part.
So just for future reference, right? Make them separate for the exam, right?
Okay.
Otherwise, it's not a free body. Right?
And I have my ins and outs. In is EA, T, FC. Out is IA, theta, and X.
Okay.
And then I just did all my truths for the circuit and the mechanical part. And then this is my reduction.
Okay. Yeah, that looks good. Slide over so I can see the opinion one. All right, yeah. You look like you're right there. Solid.
All right, and then that's kind of where I got stuck. So I didn't know if I should put in all the values the problem gave me right at this part or try to do the transfer function and then do that.
Good question. I would say my recommendation is wait until the very end to put your numbers in. And the reason is that if you are ever, if you're ever given like, or if you're ever told that any of your parameters change, then all you have to do is go back to your transfer function and pop those numbers, pop those values in, right? If you do it with numbers, you have to go back to the very beginning or whoever you inserted the numbers and then change it and run all the math again, right? So it's a little bit more upfront time, but it's more reusable on the back end, right? That'll be the only.
Okay.
Cool. All right, good stuff. So looks like you were right there, right? I changed the problem loop a little bit anyway. So even if you it right, we literally just changed the parameters. So notice I did not give omega or omega dot initial condition. I'll talk about why in a second. So there is one thing, right, that we want to do before we start taking Laplace transforms. And remember, he had the three equations, which is appropriate, but they're both coupled by that FC term, right? So we want to put them both together because we want to know what x is, right? So what we're going to end up with are these equations, right? We're going to end up with L I dot L plus R I sub L is equal to En minus KB x dot call that equation 1 T minus F C R is equal to J theta double dot equation 2 and FC is equal to MX double dot plus BX dot plus KX. And so we end up with this. These are my equations, right? And what I'm telling you is that I want to combine these before I take the Laplace transform, which isn't hard to do in this one, right? Because it'd just be solving one of them for FC and putting in the other. And really all we want to do is get rid of these theta double dots, right? This theta and theta double dot. So how would we do that, right? So if we combine 2 and 3, well, I would have T minus MX double dot plus BX dot plus KX times R is equal to J theta double dot, right? Well, that doesn't really get rid of my theta, right? So how am I going to do this? Well, remember, we know that x is equal to r times theta, and so therefore theta is equal to x divided by r. Omega is equal to x dot over an alpha is x double dot. Right? We know that, right? We know that, and if we know the position, another way to remember this is maybe you don't remember that x is equal to r times theta, but hopefully you remember that the angular velocity is equal to the tangential velocity times the distance you are away from the axis of rotation. Right? So omega is equal to v times, or v divided by r. V is equal to omega cross r. There we go. I said it backwards. I do need more coffee. Blake's right. Dang it. Next year, senior project. Learn how to print caffeine patches that I can wear during the day. Right. Leave that in your feedback for Professor Russell. Thank you. Okay, so we have this, right? So I'm going to plug in this theta. Right? Remember, this is just theta double dot, and this is just theta dot. Right? Didn't mean to use all the Greek letters all the time. So I can do this, right? And I can say, well, that means that J is just times X double dot over R plus M X double dot plus B X dot plus K X times R. This is capital R. And that's equal to T. And now I have everything in terms that I need, right? So I will just say that J over R plus M times X double dot plus BX dot, well, hold on, please. MR X double dot plus BR X dot plus KR X is equal to the input torque. What's my input torque? It's the electromechanical torque, right? It's going to be Km times R. So we'll talk about that, right? So this is equal Km times I, or we'll just call it I. If you wanted theta as the output instead, you could do the same deal, just combine it differently, right? Just go from X to thetas, right? Using the same equation. Fine. This is the equation, we'll call this 4. This is the equation that I'm going to use. I'm going to use that equation, and I'm going to use equation 1. I'm going to use those two equations, and I'm going to take Laplace transform. If I use these two equations, I do not need initial conditions for theta or theta dot, right? I just need X and X dot, like I have. So now I'm going to struggle to remember what the initial conditions are. So I'm going to go grab those real quick. Two amps, 1 meter, half meter. Okay. So there. All right, I wrote them down. We're good. I can remember them now. So first thing we're going to do, all right, is we're going to take the Laplace transform of that equation 4 that we wrote down on the previous slide. So I'm going to take the Laplace transform of this guy, all right? And now I've got to include, so now this is going to take us a second because I've got to work this out as we go. So I've got J over R plus M times R times what? Well, the first term was X double dot, right? So this is going to be S squared X of S minus S times X naught, which was 1, minus X dot naught, which was 0.5, right? So this is S X of 0 minus X dot, right? That's what we're doing. I just subbed in as we went, right? But remember, it's S times X0 minus X dot. You don't remember that? That's fine, because you have the formula for how to find this. Right? The second term that I have is B times R times S, x of S, right? Because it's the Laplace transform of x dot minus 1. Because it's x naught, right? Minus 1. Then I have KR x of S. On the right-hand side of that equation, I have Km times IL, which becomes Km IL S. And so I can start to move some of these things around and I can algebra them, right? I'll get J over R plus M R S squared plus B R S plus K times R. This whole thing times X of S minus J over R times M R minus point this thing times S. S minus 0.5 J over R plus 0.5 from R. Right, that's the first term just expanded. Plus B, or I guess it'd be minus BR, right? Minus BR, right? So I took all of my XS terms, that's the first term, right? This is everything that has to do with X of S. Then I took the remaining terms, right? This is J over R plus MR times S. That's where this comes from. It's negative because it's a negative S. Minus 0.5 J over R plus 0.5 MR because of, well, that should be negative all the way around, right? That should also be negative. Because I'm multiplying by negative 0.5. Minus BR times 1, right? This whole thing is equal to K I sub L. So this is super gross, right? Super gross. And you're going to want to put numbers. You're going to want to put numbers. It looks gross. Fight the urge. Fight the urge. Right, because I can take this stuff here on the left, the X of S, and I can move everything else to the right, right? Because that's what I want to do. This is the Laplace transform method. So I have to solve this equation for X of S, right? And that's fine, I can do that. But before I do that, right, I'm actually going to leave it in this form for a second. Because before I start moving things around, I'm going to solve equation 1 for IL and flip back. Because I want everything, remember, I want everything from the input to the output. I want everything from E in to X. And everything has to be in terms of just E in and X. That's what I want. So we're going to put a pin in this one for a second. Right? We'll come back to it. Why don't we call this Laplace 1? Oh. Okay. So the other equation that we're using, right, is L I dot L plus R IL is equal to En, right? That's what we're using. So, okay, take the Laplace transform. What's that? Oh, yeah, sorry. Minus KBX dot. Take the Laplace transform. If I take the Laplace transform, this becomes, well, that's going to be LS IL of S minus 2 times LS. Or not 2 times L, no LS. Why? Derivative. The first derivative. S times the function minus the initial condition. The initial condition is 2 amps. Right, L is a constant. I'll get put back in. Great. Plus R, IL of S, equal to E N minus K B. Well, X dot's going to be S, X of S minus K E, right? Because remember, this is X naught, and this is I naught. I can solve this for IL, right? So let's combine like terms. Now I have something in terms of IL of X. And I can take this and I can plug this in to equation L dot 1 on the previous slide. And you can see this is going to get fun real quick. Real quick. We're now beyond the point where my notes are actually going to help with this problem, right? Because now this looks nothing like the transfer function. Right? With the transfer function method, you get rid of those final two terms in the numerator, right? They're gone. They're out of here. All right, everybody cool so far? You following? So first part of the Laplace transform method is get your model, get your equations, right? The second part is take the Laplace transform of them. The third part is combine them if you need to, right? So now we're going to combine them, right? So the algebra intensifies, right? Let's see what happens here. Okay. So please hold. Actually, let you guys look at that. Please hold for a second. I don't feel like rewriting both of these things, to be quite honest with you. Okay. And grab this one. And we're going to go. This is gross looking. All right, this is gross looking. So we grabbed both, I got both my equations. Right? I'm going to take that equation L2 and I'm going to substitute it into equation L1. If I can find my pen. I'm going to try to use my best handwriting here. No promises. Easy, easy peasy. Beautiful, beautiful, glorious, right? Oh, goodness. All right, so now what do we have to do? Well, now we solve this for x of x, right? How are we going to do that? Well, first thing we're going to do is we're going to multiply through by ls plus r for every single term. So, I want you to see what's going to happen here. Okay? If I multiply through by ls plus r on this entire thing, this is going to give me a third order system, right? Which is what we expected because we started with a first order circuit and a second order mechanical system, right? Ish. All right. All right, let's go. Man. I don't even know anymore. The question was, would this be something that is messier than what you would see on the exam? And honestly, I mean, this is kind of like third order system is kind of like the highest that you would have to mess with. This one because it has so many parts and so many combinations, right? You've gotta go around and do, right? It does complicate things. If you don't do, right, so I just want to point this out. If you did it the way that we originally intended, I intended this problem to be done, you lose this term, all of these terms over here, right? Like you lose 5 terms out of this. So in the transfer function method, when you don't have to consider the initial condition, it cleans this up significantly, right? Cleans this up significantly. All right, so actually this should look the same as this one, except with just these extra pieces, right? So it's fine. So third plus LBR S squared plus KL R S plus R times J over R plus N S squared. E squared plus squared. This whole thing is this. Equal to L over I'm not gonna have enough room here. All right, pause. Yeah, I didn't want to do that. All right, pause this for a sec. I'm gonna run out of room. Okay. Yeah, no, right? Jeez. Yeah, so that plus plus R times that. I would like the next slide, please. Thank you. Plus. Okay, that takes care of the mechanical side. Now the other parts are KMEN. All right, these just stay the same as they were. So let's do this. I like perfect. There's a leave that there. I'll rewrite it. And so this should be capital, right? So there it is. Right. Last thing we have to do is we have to add our KM KBS back over, or we got to add this term right here. This guy has got to go back over to the other side to get all the X's on one side. Alrighty. So if I add this back in here, right? Really trying to think of the best way. I don't want to rewrite the whole thing again, but I'm gonna have to. Right. So adding this back in just puts a Km times Kb plus S, or Km times Kb times S, right? If I move this into here, right, that's just gonna add that Km KbS in there, right? So we can actually, and I'm gonna try to do this like this. So X of S should actually equal that whole thing divided by there. That's what x of s is. Now we plug the numbers in. Okay. Once we plug the numbers in, this will look a lot more manageable. Right? Because all of our variables will go away. So let's do that. And S. All right. So far, so good. Hold on. My bad. S cubed. S squared. Hold on. Wait a second. Forget that part. It's the same. I know this is riveting. You guys have any questions as we're going? I'm just plugging in numbers and trying to get this out. You have anything you guys want to talk about? We're almost there. Okay. Sure. Yeah, that's true. So why wouldn't you do this over SFO? Right? Well, first, you gotta remember the way that I wrote the problem was using the transfer function method, which eliminates most of the things that are just like cluster. Right. Secondly, base case is nice, right? And it certainly work. 61 half dozen the other. Mainly because you guys haven't taken linear algebra and you didn't know how to solve it by now. Okay. So we got to take all of this and add it all up. So, well, at least it's pretty clean on the top. Let's see, 2 plus 24, 4, 6, 5, 6, 7, okay, so wait, you get there. So x of s is equal to well, sorry, I'm just rewriting. Start there. Was 792.78. Put on the okay. Almost there. Oh, there we go. So there we go. 51.2 S cubed plus 233 S squared plus 499 S plus 1.2. We did it. We got it. Is it right? I have no clue. We're gonna go with it at this point because we've got 10 minutes left in class. So what do we do? Now that we've got this, what do we do? Now we do partial fraction expansion, right? Except that we need E n of S. So what's E n? E was a, oh, tell me, it's a step of 12 volts, right? So 240 over S, right? Okay, that's En. Fantastic. That's just great. You know what? We're going to change it, and we're going to say that it's a delta of 12, because I don't feel like rerunning all of those numbers. So En, right? I don't feel like putting that in right now. Say it's 12 delta. Great, perfect. All the cameras. Okay, so now we've got this. Fantastic, right? And that would help us simplify because negative 108.78 plus 240 was just going to give us, it's going to change this to 131.2. Okay. Roots. What are the roots? All right, well, let's find the roots. Good news, maybe. I'll put this in. Uh-oh. So we've got one real and a complex conjugate. It's not really right? We can handle this, but we're not going to have time to run through the partial fraction. We've got 7 minutes left in class, and we all know that ain't going to happen. Let's be honest with each other. Right. I'm going to post all the solutions. The one that I did in my notes looks nothing like the one that we just did because I changed the parameters. I should know better than to change parameters on the fly, but we almost got there. We almost got there. So what do we do, right? Let's just quick recap, right? I'm going to call all of this right here. I'll call this num. I'm going to call all this 10, right? Cool. X of S equals numerator over denominator is equal to, well, A over S plus 0.002, which, by the way, is an extremely slow part of our system, right? This is going to dominate hard. because the time constant is 1 over 0.002, which is 500 seconds. So, I mean, that's, or days, or years, or whatever unit of time happens to be, millennia, right? Plus BS plus C over, whatever is left here. I don't even know. That's 500. Right. Over, what's probably going to look like this, right? Because we need to make it look like that. So you run through, you find A, B, and C. Then you do a second partial fraction expansion to make sure that you know how much of it is the sine, the gap sine, and how much of it is the gap cosine. Then you're done. Then you inverse Laplace it. So we should be getting something out of this, right? Should be getting something out of this that takes the form of A e to the negative 0.00 to t plus b. It doesn't really. B sine 2.1 or t e to the negative e to the positive 2.2 or negative. Where is Dr. D grabbing these numbers from, right? Is he making them up? Remember, when you look at the roots, the real part gives you the exponential, and the imaginary part gives you the frequency, right? So we should get something that looks like this. I might have messed up B and C in terms of which one goes with sine and which one goes with cosine. In fact, I probably did mess that up. But that's how we do it, right? Yeah, I suppose. You guys have any questions? So many questions. Guess what? Office hours from 3 to 5 tomorrow. If you need me earlier in the day, you can shoot me a private message or a Discord message and see if I'm around. And I'll try to, if I'm not doing anything else, I will hop on Zoom and we can talk about things, right? Now that we did all that, and everybody feels nice and good and happy, how are we feeling? How are we feeling about that? If you're in the bottom half, as usual, right? If you're in the bottom half, you gotta come to office hours. You gotta let me know how I can help you. Right? I can't help you if you don't tell me what you're struggling with. Okay. Remember, Monday office hours 9 to 11. One of the other students asked if I could do them in a different location. I will be on campus on Monday. Normally I'm not. So I'm going to be in room 1345. First 12 students who want to show up and sit inside for office hours. If it gets bigger than that, we'll do it outside. We'll get the arena and be fine. Yeah.
What time was that on Monday?
Monday, I've got 9 to 11 a.m.
Okay. Cool, thanks.
These problems just take time, right? That's like, it's literally, if you look at the skills that we use to do that, is all algebra, right? It's we just gotta take the time to do the algebra. What's up, Austin? That's right. When do you start? Where do you start? What is the day of the week is that? Can you take it on Monday? Yeah. Yeah. Calendar. Okay, so When are you free on Monday? Okay, why don't we say, look at my Monday. How about from 2 to 4:30? Yeah. Okay, why don't we do that? I'll give you a Zoom link to join, and I'll give you the code. Yeah, I'll shoot you this right now.
And for the lab,
Mhm.
Crystal will transmit it and it will transmit it to a flag first submission.
Gotcha. Not, no, yeah, thank you for letting me know. Don't worry about it.